Okay, let's get started. So just as a reminder, I'm going to go to section tomorrow, just the later one, so the 1221, just to observe the TA and give her feedback. It's part of her training. Just so that you all know and you're not wondering like why I'm there. And then also as part of her training on Friday, she is going to be doing the lecture, and I'll be observing that as well. So for today, we're going to continue talking about derivatives. So I wanted to do one more example of computing a derivative that's a little bit more involved. So let me just remind you what the definition was. So recall, if we have a function f of x, then we define f prime of x, which is called the derivative of f, to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And the idea behind this was that if I plug in any particular value of x, then f prime will tell me the slope of the tangent line to the graph at that particular x value. And the reason why that is described by this limit, you can just sort of remember this with a little picture. So say this is the graph of my function, and I want to know what the value of the slope is at this particular x value, then I can look at another point that's nearby called x plus h. So that distance h is going to go to 0, and look at the line in between those two points. And as you drag that pink point closer and closer to the blue one, you will approximate the true tangent line. And then, so this expression here is just the slope of this green line. So it's change in y divided by change in x. Okay, so this formula hopefully is not too mysterious. It just comes from the fact that we're trying to compute the slope of the tangent line as a limit. Okay, are there questions about that? Anything that came up between the last lecture and now? Okay, so let's do an example. So let's find f prime of x, where f of x is equal to x cubed minus x. So we just have to write down this limit. So we'll have f prime of x is equal to the limit as h approaches 0. And I'm just going to go ahead and plug in everything to f of x. So first we have f of x plus h. So I have x plus h cubed minus x plus h. And then we're subtracting off f of x, which will just be x cubed minus x. And then that's all over h. Okay, so now we're just going to have to expand this out, and then hope that there will be some kind of cancellation, and that will allow us to get the h out of the denominator. So let's go ahead and do that. This will be the limit as h approaches 0. Yeah. So yeah, so what happens is, right, the derivative is only defined to be this when this limit exists. So if the limit does not exist, we're gonna get into this later, but if the limit does not exist, then the function is said to be not differentiable at that point. So typically, like if your function is differentiable, which like most nice functions are, you will be able to either cancel with something in the numerator or otherwise like resolve that h being in the denominator. And if you can't, then that means that the function's not. Yeah. So, but like if you look at the function, like you look at this and you're like, okay, this is like a pretty nice function. You should expect that there'll be like, yeah. Are there other questions? Okay, so I think there's two ways that you could expand this out. One is to just remember what happens when you cube something with two terms in it, which is sort of how I do it. But another way that you could do this is just do it in 2 steps. So you could just first FOIL x plus h squared, and then again multiply that by another copy of x plus h. So but yeah, so here's like how I would do this. So I just remember that we get x cubed plus 3xh plus, x squared h plus 3xh squared plus h cubed minus, so that was all of this stuff. And then for the rest of it, we'll get minus x minus h minus x cubed plus x, and then we're dividing that by h. Is have you guys seen the binomial theorem before? It like tells you, so this is like as an aside, tells you like if you have x plus y and you want to raise that to any power like k, it tells you how to do that. Is that something you've seen before? So if that is something you've seen before, that's like a quick way to do this. Yeah, but like I said, otherwise, like if this isn't something that you've seen before, then you could just do this in multiple steps, like just multiply out x plus h, like 2 at a time. Okay, so let's cancel things. So we get x cubes canceling, we get x's canceling, and then I think that is everything. Right, so nothing else simplifies. Okay, so then I get the limit as h approaches 0 of 3x squared h plus 3x h squared minus, oops, sorry, there's an h cubed there too, plus h cubed minus h, all over h. And then we can just apply the switcheroo to cancel out the h's from the numerator and the denominator. So we get the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1. Okay, are there questions so far? Are we good up to this point? Yeah. Like, why did we start out with this h here? Yeah. Okay, let's look at the, let's go back to this picture. So if we wanted to write down the slope of this green line, then we could just do change in y divided by change in x. So change in y would be f of x plus h minus f of x. So that's where we get this from. And then the change in x would be x plus h minus x, which just simplifies to h. Oh, wait, no, so it's on, so it passes through A because A is in the.
So here, okay, so A, I don't have an A here, I just have X. So we're like looking at what is the value of this slope at like this X value. And so basically H, you can think of this as just like the distance of another point from X, and then we'll just send that distance to 0. Okay. Are there other questions? Yeah.
Like, show the switcheroo gets rid of the h's, because I thought you can't divide unless you're multiplying them.
Okay, so everything in the numerator has at least one factor of h, right?
Okay.
Yeah. Are there other questions? Okay, so now if we look at this, so this appears to have multiple variables in it. So you just have to ignore the x's, and we're thinking about this as a function of h for the moment. So, you know, if I plugged in any particular x value, like x equals 5, this whole thing would just be a polynomial in h. And so we know that polynomials in h are continuous functions, and so we can just plug in h equals 0 to find the limit. So this is 3x squared plus, this one is 0, the next one's 0, and then we just have -1. So this is because this is a polynomial in h, so we can plug in h equals 0 to find that limit. Okay, are there, yeah, do you have a question?
Yeah, sorry, could you repeat what polynomial?
Yeah, so, okay, so something is a polynomial in h if it has terms that are given by like h raised to some power times some coefficient, and then you just add up some number of those terms. So like, what are we gonna do with this? We're gonna like plug in, you know, with the derivative, we want to know what this is at particular values of x. So you could think about like if I plugged in some specific x value, these would just be numbers, right? And so then what I'm left with is just a polynomial in the variable h.
And where it doesn't have h, you would just say, well, it's just h.
Yeah. Yeah, did you have a question? No. Yeah, we'll do some examples, yeah. But like, so for example, like the graph of absolute value of x, like it has like a kink in it at x equals 0, so you won't be able to find the derivative there. Yeah. No, because like, okay, so well, this is like the next example, but like if you think about what the left and right limits are, like the limit of the slope, they're gonna disagree at that point. So the limit won't exist, even though the function's continuous there.
Oh, like, when they're both approaching, they are.
Yeah. Yeah. Is there, yeah.
So just confirming that when you're plugging in h equals 0, people think the polynomial
Yeah. So yeah, polynomials are continuous functions, and if you're taking the limit of a continuous function, you can just plug in the dot.
Okay, good. Let's just, I'm gonna graph these two functions so we can just take a look at some of the features of the graphs. So on the left, I'll put f of x, which was x cubed minus x. And then on the right, I'll put 3x squared minus 1. So x cubed minus x looks something like this. And then 3x squared minus 1 looks like this. I drew that a little lopsided. Okay. So I just want to like observe some features of these graphs. So one thing is that when this has a horizontal tangent here and here, that's when this is going to have a 0. So one thing we notice is that, like, so if I have a horizontal tangent, let me make a little dictionary. The horizontal tangent in F corresponds to a 0 of F prime. Does that make sense? And then you can think of this purely just in terms of the slopes, right? Like a horizontal tangent means slope is 0. Slope is 0 means F prime is 0. And then another thing is whenever I have positive slopes, so when my function is increasing, that corresponds to when the graph of F prime is above the x-axis. So so I get that F is increasing corresponds to whenever F prime of X is greater than 0. So let me color in those parts of the graph. So we're increasing here and here, and we're above the x-axis here and here. And then the other thing, which I'll just leave blue, is if F is decreasing, that corresponds to when F prime of X is less than 0. So yeah, if you are given a graph of any function, you can start to sketch what the derivative of it might look like just by thinking about like what are the slopes of the tangent lines at various values. And I think like conversely, we can learn something about this. So like if I just give you x cubed minus x and ask you to figure out where are the horizontal tangents, it's not clear maybe at first how to do that, but then if you think about it, you can just take the derivative and solve for the zeros of this polynomial, and that will tell you where those horizontal tangents are. Other questions? Yeah.
I'm thinking about like a fineness for life. So like I was thinking about like finding the derivative at a point. So then if something, for example, is a polynomial, it would be like being like rotation during running. But like I was thinking, for example, if light hits like a mirror at a certain angle, and then refracts, then that would be the absolute function. So then at that point, that's an example of when it cannot be differentiated.
Yeah. Yeah, good. Okay, let's talk about when a function is differentiable and do the absolute value example, and then also we'll see, I'll give you sort of a list of like other ways that a function can fail to be differentiable. So here's the definition. So a function f is differentiable at, let's say, a, if this derivative f prime of a exists. So what I mean by this is like this derivative is a limit of something. So if that limit exists, then
you know, you can say f prime k exists.
So, and then you also say if it's differentiable for every value inside of some interval, then you would say that it's differentiable everywhere on the interval. So if f is differentiable for all a in some interval or even just a subset of R, then you can say that f is differentiable on the interval I, or just the set I. Okay, so let's do this absolute value example. So let's let f of x be equal to the absolute value of x, and we'll find where is it differentiable. Okay, so let's write down the definition of absolute value of x. So we have that the absolute value of x falls into a few cases. So when x is positive, the absolute value of x is going to be equal to x. So this is just x when x is greater than 0. And then for negative values, the absolute value of x is going to be negative x because you need to multiply it by a -1 to get the value. So, and then when x is 0, this is 0. Okay, and the graph looks something like this. Okay, so we're gonna find the derivative and figure out where this is differentiable. To start, we could look at this graph and just think about the fact that the derivative is supposed to be telling me what the slope of a tangent line at a given point is. So you could draw already the graph of f prime of x just from this picture. So in this region, the slope is always just going to be 1, right? This is just a line with slope 1. So I get in my picture of f prime of x, I get slope 1 for positive x values. So I'll put a hole there for now, but we don't know at the moment, we don't know what happens when x is 0. And then similarly, for negative x values, this is just a line with slope -1. So we get a slope of -1 here. And then at x equals 0, it's not really clear what's happening, right? Like what the slope should be at that point. So here, I think we just have like a question mark for like what the value of this should be. And like the preview is that it's going to turn out to be that you know, the function is not differentiable at this point, but let's like see why. So right, we want to compute the derivative, so we'll be taking the limit as h approaches 0 of absolute value x plus h minus absolute value of x divided by h. And since our function is a piecewise function, we're going to have to break this up into cases in order to you know, be able to do any arithmetic with these absolute values. So I'm gonna look at these cases. So the first thing that I'll look at is whenever x is greater than 0. So in that, so this is like the first case here. So their absolute value of x is equal to x. So I can rewrite this limit. This is equal to the limit as h approaches 0 of x plus h minus x divided by h. This is this limit. And then the x's cancel each other, so we get limit as h approaches 0 of h over h, which is just the limit as h approaches 0 of 1. By the switcheroo, we can just cancel the h's, and then we get that this is 1, which is what we thought from the picture. Okay, are we happy with this first calculation? So now I'll do the case when x is less than 0. So here, the absolute value of x is equal to minus x. So then we get the limit as h approaches 0 of minus x plus h minus x divided by h. So how does this simplify? We get the limit as h approaches 0 of minus x minus h plus x divided by h, which is the limit as h approaches 0 minus h over h, which just gives us limit as h approaches 0 of -1, which is -1. And that's also what we expected from the picture we drew. Okay, so one question you might have is like, why am I treating x equals 0 as a separate third case? Like, why not just lump it into one of these? And the reason is because you think about like how we define limits, we had the left and the right limit and we wanted them to agree. But in this case, the function is actually like different when for the left limit and the right limit, right? So if I'm looking at like what's happening for values as x approaches 0 from the left, that is like a separate case of my piecewise function when compared to looking at values as x approaches 0 from the right of this function. So that tells me that if I want to compute the limit at x equals 0, I'm actually going to have to compute the two one-sided limits and check whether or not they are the same. Does that make sense? So now I'll do the third case, which is the x equals 0. So I need to do two one-sided limits and see if they agree. Okay, so if I take the limit as h approaches 0, say from the left of absolute value x plus h minus absolute value of x all over h, so I'm gonna plug this in for when x is equal to 0, right? So I'm gonna replace in here x with 0, just right over this. Okay, so this gives me the limit as h approaches 0 from the left, absolute value h divided by h.
Does it make sense? Why this is the limit that we're looking at? Yeah,
Yeah, I guess I'm confused, like, why it's, say it, like, being, the case where x equals 0 is ported off as its own case that just applies to x equals 0. What does it even mean to take a limit if, in some sense, there's no, it's not.
I don't know if I understand your question. So, so when
Let me just like rephrase the reasoning for why we need to do x equals 0 as a separate case. So if I want to look at, okay, so the limit that I'm looking at when I'm taking a derivative is some expression involving the function, right? So, you know, we have to look at this limit. So for values of x, where x is, you know, like firmly planted in one of these cases, I can say what the absolute value function does. So like if x is positive, then these numbers will be, as long as h is close to 0, will definitely be in this case. So I can just, as we did here, like remove the absolute value. It doesn't matter like if I'm coming from the left or I'm coming from the right, we're just going to be in this case. But if I'm looking at the limit when x is equal to 0, so let's like plug in 0 there, then like for example, this could be a positive number or a negative number depending upon if I'm taking h's from the left or the right. Yeah, so the two limits could be different. Does that make more sense or address your question?
Everything you said makes sense. I guess I still have a question I had before, but
Okay, maybe we can talk after. Yeah. Okay, so we're computing this limit from the left. So my values of h are coming from the negative numbers. So that means that absolute value of h is going to be equal to negative h. And so again, we get, for this limit, we get -1. However, if we compute the limit instead for h is coming from the right, so if I do limit as h approaches 0 from the right, absolute value h over h, this is going to be, so now h values are positive, so we get limit as h approaches 0 of h over h, which is 1. So the left and the right-hand limit do not agree, and so that means that the limit does not exist. So f prime of 0 does not exist because the left and right limits do not agree. So that means that f is not differentiable at x equals 0. So the answer, so the original question was, where is f differentiable? So the answer is absolute value of x is differentiable on, we have the interval from minus infinity going up to 0, then not including 0, union the interval starting at, positive numbers, but not including 0, all the way up to infinity. Yeah. Oh, that refers to the derivative of f. So if you have any function, f, g, whatever, then you just write like f, you call it prime, f prime is the derivative, or like g prime or whatever. Yeah, other questions? Okay, let's look at some other ways that functions could fail to be differentiable. Or just like make a list of ways functions can be differentiable or can be not differentiable. So one would be if they're not continuous, that will fail to be differentiable. So if we're not continuous. So say you had like a jump discontinuity or something like that, then you won't be able to take a derivative at that value. And like we just saw, also if you have like corners or kinks, so like we had with the absolute value function, you can't take the derivative at this point. And then another thing that could happen is, so we also saw that limits don't exist when the limit goes to infinity, right? So if you have like a vertical tangent, then that's also not differentiable. So if you have a vertical, so, and this is like kind of hard to draw, so let me see. So like the idea of this drawing is this is supposed to still pass the vertical line test, like it only passes through this point once, but it the value of the slope goes to infinity there. So if you have something like this. And you can play around with this and try and do some other examples. Yeah, do you?
Yeah, I'm confused on the first one.
Yeah.
So, like, yeah, I guess intuitively, I would expect that to be flat line. Continuity with like the same slope feels like the first derivative is just slope of the line, like it is kind of like the same in some sense. Line. It feels like there should be something. What do I get? When like it feels like you could basically take any function and just put like just stick like a random like this continuity in it, where as long as the slope is still kind of the same, except for that, like term you basically added, like the derivative would actually still just look the same, right? Like it would still be the same, even I guess at 0.
I see what you're saying. Like if we computed the limit of the derivative coming from this way and the limit,
Yeah.
defining the derivative coming from this way, for both you would get 0. So,
Yeah, and then like more generally, I suppose that you could just turn like any function that's like above a, you can just stick a. That.
sure. Yeah, do you have a comment or a different question?
I was thinking about that. Then I was sort of thinking about it in like a real life example. So for example, like if there's a straight line, and we're like biking like a path,
Mhm.
and then suddenly there's a drum that's continuity, meaning that the path doesn't exist. So it's because like there's that discontinuity. So technically you don't have a speed on that point that doesn't exist. So that's why it's not.
That is a good intuition, but we should be able to see from the definitions why this is not differentiable. I think I need to think on this. Yeah, so I'll like post a I'll post an announcement or something explaining this, but like for sure this is not differentiable, but I think like we need an answer as to like why. Yeah. Okay, good. Other questions? Okay, one thing I wanted to mention was that we can take what's called higher derivatives of a function. So if you have so say you have a function f. So if f is a function, then we've been talking about how to take its derivative. So we get this new function f prime. So if it has a derivative f prime, then you can also view f prime as like a new input function to which we could again take the derivative. Then f prime is also a function and we can take its derivative. So here's an example. So here's how you would write it. You would write it as f double prime. And then you can continue if you like, and you could take the third derivative, or as you start to add more primes, it's more typical to just write the number of derivatives like in parentheses as an exponent. So like this means like take the derivative 5 times, for example. So let's compute an example of this. So we'll find f double prime of x if f of x is x cubed minus x. Okay, so we already know from the example at the beginning of class that f prime of x, so we already found that f prime of x is equal to 3x squared minus 1. So yeah.
Yes, but on tests, we have to write like the full form derivative, like the one derivative, or can we just like do it like how we like figuring out how we.
Okay, yeah, this is a good question. So on Friday, we will get better techniques for taking derivatives to where you won't even need the limit anymore. So it'll just depend on the question. Like probably the way that I would phrase it is just like take the following limit, but it might be a limit that does actually compute a derivative.
But yes, for the most part, like you will learn or may already know just like rules that make it a lot easier to take derivatives. And we'll do those on Friday.
Okay, so we can compute this limit, so this derivative, so f double prime of x will be given by the limit as h approaches 0 of f prime of x. Sorry, f prime of x plus h minus f prime of x divided by h. So we'll just do this. So we'll take the limit as h approaches 0. So I'm just going to plug in x plus h into f prime of x. So we get 3x plus h squared minus 1. And then we're subtracting f of x as well. So we get 3x squared minus 1 divided by h. And then I'll expand this. So we get the limit as h approaches 0 of 3x squared. And then when I FOIL, I'll get 2xh's, but then I'm also multiplying by 3. So I get 6xh's plus 3x squared minus 1 minus 3x squared plus 1 divided by h. Okay, and then, oops, I made a mistake. That should be an h. Okay, so then now we get cancellation. And we are left with the limit as h approaches 0 of 6x. Maybe it'd be helpful if I actually factor out the h. So we get h times 6x plus 3h, and that's it. Divided by h. And then with the switcheroo, this is just the limit as h approaches 0 of 6x plus 3h. This again is a polynomial in h if we just ignore the x's. And so I'm just left with 6x. Okay, are there questions about this? So on Friday, like I said, you'll get some better methods for taking derivatives where you won't have to look at the limit anymore. I had a teacher in high school who was like truly just like a character, but he would always say mathematicians are notoriously lazy. And what he meant by that was like this is too hard. And so we're gonna like put in a little bit of extra work to find a better way to do it, which will allow us to be lazy in the future. So we don't have to, you know, invoke limits every single time we do this. Okay, so I'll stop there for today and see you all on Friday.